All right, yes, Prep family, here it is. It's been a while since I've done an instructional video. This one is Unit 5. The way we organize the curriculum at Yes Prep. In Unit 5, this is when we talk about special topics in differentiation and integration. And so that you understand sort of big picture where this fits. Normally this is the unit that I start after Thanksgiving break. Students are proficient in all the derivative rules. Product rule, quotient rule, chain rule, all the trig derivative rules. We've got that. We've also done a unit on the definite integral where we've done some application problems, but we do not know actually how to find an integral, the value of a definite or an indefinite integral, without using the calculator. So that's sort of where we are. Any integration problems that we're going to see in this video will be done using the graphing calculator, because that's where we are in our understanding of the integral. If you're watching this later in the course and you already know these integration techniques, well, some of the functions are still really difficult to evaluate without the benefit of a graphing calculator. So let's get started. My hope is to do this as one continuous video versus the 5 or 6 different segments that then get posted. So I'm going to try as best as possible to just, if a mistake is made, we'll fix the mistake and kind of power through this. So let's look at the big ideas that we encounter in this unit. We've got the average value of a function is the first big idea that students are presented with. We'll look at the formula for that and do an application problem. Then we're going to come to the mean value theorem, which is, I think, still a very misunderstood and misapplied theorem. We have the fundamental theorem of calculus. This is the first time it shows up in the course. We're going to look at some physics problems, specifically looking at displacement versus the total distance traveled. We're going to finally unearth some of the properties of integrals, and then finally we're going to do a rate function, actually that involves multiple rate functions, and again that's going to be very calculator heavy. So let's get started with the first theorem. We have the average value of a function, and the average value of a function, in order to find that, if we have a function that is on a closed interval, so there's your interval a to b, then the way we find the average value is we find the definite integral from a to b of f of x dx. We understand that to mean that's the area bounded by the curve f of x from x equals a to x equals b, bounded between the curve and the x-axis. And then we have the multiplication factor. We're going to multiply by 1 over the length of the interval. So average value of a function on a to b, 1 over b minus a, integral from a to b, f of x dx. That's the theorem, that's the formula that you need to know whenever you see average value in a calculus class. That's the way we're going to do it. So let's look at a problem. We've got a function shown at the right. We want to determine the average value, okay, so that's already my first clue, for the function on the interval -3 to 6. The portion of the graph from x equals 0 to x equals 4 is a semicircle of radius 2. So what I train my students to do is, as soon as you know it's an average value, well, we're going to be integrating some function. Now from where to where? I want the average value on the interval -3 to 6, and I'm going to multiply by 1 over 6 minus -3. Sometimes, depending on the exam question, just writing that expression down can earn you some points. Now, where do we go from here? I can simplify this to 1/9, the antiderivative from -3 to 6, f of x dx. Okay, so I need the definite integral from -3 to 6. If I go over to the graph, what that means is I want to find the total area bounded between -3 and 6. Since we've already done this in the previous unit, we're really good at breaking the region up into different known geometry shapes. Here we have a triangle. The base of the triangle is 3. The height of the triangle appears to be 6. Area of a triangle, 1/2. The base times the height. And we're going to get 9. Now we get another triangle over here. The base of this triangle is 2. The height of this triangle is 6. 2 times 6 is 12. Cut that in half. We get positive 6. Now we need to go to this last piece. And if you read the prompt carefully, well, you were told that that portion from 0 to 4 is a semicircle, so half of a circle. The radius is 2. So if I know the radius is 2, the area is going to be 1/2 times pi times r squared, or 1/2 times pi times 2 squared. If I do that, 2 squared is 4. Cut it in half, we get 2 pi. And I want to be careful, because we are below the x-axis, that's going to be a negative area. So, to find the average value, I take 1/9. The total area from -3 to 6 is 9 minus 2 pi plus 6. You could stop there if you want to, or you could combine the 9 and the 6 to get 15 minus 2 pi, divide the whole thing by 9. If you're on the free response part of the exam, you can stop here or you can stop here. It doesn't matter. On the multiple choice, this is much more likely. And really, that's all you do. 1 over b, you find the definite integral from a to b, 1 over b minus a, done. Okay, that brings us to the mean value theorem. Couple of things to make sure if you are going to apply the mean value theorem, or if you are tempted to apply the mean value theorem, you must show or know that the function is continuous on the closed interval. So continuous, no holes, no jumps, no breaks, no vertical asymptotes. And differentiable. Differentiable means that the derivative exists everywhere on the open interval a to b. Another way I tell my students to think about differentiable, smooth, right? A nice smooth curve, like a polynomial, the trig functions. As long as there are no sharp points like you get in the absolute value, if there are no vertical tangents like you get in the cubed root of x, then your function is differentiable, and now you can apply the mean value theorem. What the mean value theorem states is that if you have both of these conditions, then somewhere inside the interval, c is between a and b, but we're not including the endpoint, then f prime of c will be equal to f of b minus f of a over b minus a. The expression on the right, f of b minus f of a over b minus a, is the slope of a secant line. F prime of c, we know that to be the slope of the tangent line. So if I'm going to use the mean value theorem, what the mean value theorem states is if I have a continuous function on a closed interval that is differentiable on the open interval, well then if I find the slope of the secant line, we always call this secant, if I find the slope of the secant connecting the endpoints, then somewhere in between here, if the pen represents my tangent line, I'm going to have a tangent line with the exact same slope as the secant line. And that seems to occur right over here at this point. So that's the tangent line I'm interested in. The slope of the tangent line equals the slope of the secant line. The value guaranteed by the mean value theorem is right here. That's x equals c. So let's actually do a problem involving the mean value theorem. I'll kind of show you how it flows, what is essential, what is the unforgivable sin in a free response question is you must show or state or know the function is continuous on the closed interval and it's differentiable on the open interval. If you don't state both of those things, you cannot use the mean value theorem, and lots of students lose points here. So you want to make sure that is really, really clear. Okay, so here we go. We have a function. The function is f of x equals, it's the rational x divided by x plus 1 on the interval -2 to 2. I want to find the value of c guaranteed by the mean value theorem, or explain that the mean value theorem does not apply. So, if I'm going to use the MVT, your mean value theorem, first of all I need to know, is f of x continuous? Well, because it's a rational function, I know that f of x equals x over x plus 1. There's a vertical asymptote at x equals negative 1. Since I have a vertical asymptote at x equals negative 1, the function is not continuous on the interval in question. So I have a vertical asymptote at x equals negative 1, therefore not continuous on the interval negative 2 to 2, which implies that the mean value theorem does not apply. Does not apply. Okay. So let's go a step further with this. Let's actually change the interval so that we can go a little bit further. So we're going to have the function f of x, same function, x divided by x plus 1. We're going to look now on the interval 0 to 2. And I want to see, does the mean value theorem apply? And if so, what's the value of c guaranteed by your mean value theorem? We've already established earlier that we know this function has a vertical asymptote at negative 1. Because I've changed the interval, negative 1 is not in that interval. So now the next move would be, let's check to see, does the derivative exist? So we're going to take the derivative. And the derivative of x divided by x plus 1, that means I'm going to need to use my quotient rule. I take the derivative of the top times the bottom, minus, leave the top alone, times the derivative of the bottom, over the denominator squared. The numerator, x plus 1 minus x, the x's cancel out, and we get 1 divided by x plus 1 squared as the derivative. Now, in order for f to be differentiable, the derivative must exist everywhere inside of this interval. When I look at my derivative, the only place where I could potentially have a problem with this derivative happens when the denominator is equal to 0. That happens if x equals negative 1. And that is not in the interval in question. So my function is continuous on the interval 0 to 2. We're happy. It's also differentiable on the open interval 0 to 2. Happy with that. So the mean value theorem applies. And our job now is to find the value of c. The special value of c, we need to find the slope of the secant line. So f of 2 minus f of 0 over 2 minus 0. F of 2, we go back to the original, that's 2/3. F of 0, 0 over 0 plus 1 is 0, over 2 minus 0, which is 2. I get 2/3 divided by 2, 1/3. What I need is I need the value of c such that f prime of c is equal to 1/3. So I'm going to take my derivative expression and I'm going to look at 1 over c plus 1 squared and see where is that equal to 1/3. I can cross multiply. I have a proportion, so we get 3 equals c plus 1 squared. I can take the square root of both sides, remembering that we get plus or minus the square root of c. Square root of 3 is equal to c plus 1. And so now I get the answer c is negative 1 plus the square root of 3, and c equals negative 1 minus the square root of 3. Now, before you do the happy dance and just think you're done, you need to make sure that both of these are in the original interval in question. We're interested in the interval 0 to 2. Well, the square root of 3 is about 1.7. It's between 1 and 2. Negative 1 plus 2 is going to be greater than 0 but less than 2. That works. Because the square root of 3 is about 1.7, negative 1 minus the square root of 3 would be negative 2.7. That is not in the interval. The only point that we're interested in, the only value of c guaranteed by the mean value theorem, is negative 1 plus the square root of 3. Okay, that was definitely a lengthy problem, but it is important that we get all of this down. It might be worth watching that part of the video again. Okay, let's keep plugging along here. We also encounter in this unit the fundamental theorem of calculus. And the fundamental theorem of calculus, we use it so much now, I think we forget there was once a time where we didn't understand this. So, you have a continuous function f of x, this is little f of x, on the closed interval a to b. If big F, I mean the antiderivative of little f. Okay? Big F is the function that when you integrate f of x, the answer is big F. Okay? Then, the value of the antiderivative at the end of the interval, this is big F of b, is equal to the value of the antiderivative at the start of the interval, big F of a, plus the definite integral of the original function from a to b. So one more time, the value of the antiderivative at the end of the interval is equal to the value of the antiderivative at the start of the interval, plus the definite integral of the function over the interval a to b. You can rearrange the terms if you would like. You can move the f of a to the other side. And what you'll get is that the definite integral of f of x dx, so the area under a curve, is equal to the antiderivative evaluated at the upper limit of integration minus the antiderivative evaluated at the lower limit of integration. And so this is something that we also use a lot, especially in the unit when we were looking at the integral as a function. So, we'll definitely be using that. Also, when we talk about our physics, previously we've looked at position, velocity, acceleration, and we know that if you have position, if you have velocity, and if you have acceleration, we know that there's a derivative connection. If I take the derivative with respect to time of position, I get velocity. If I take the derivative of velocity with respect to time, I get acceleration. We've also started to look at, if you're given the acceleration and you want to get to velocity, we're going to take an antiderivative. If you have velocity and you want to find the position, you take an antiderivative. But additionally, we know that the displacement, if you have an object moving with a velocity given by v of t, if I take the antiderivative from a to b, that's how I'm going to determine the displacement. So one more time, the displacement of an object from a starting point A to an ending point B, the displacement is found by taking the definite integral from a to b of the velocity function. However, if we want to find total distance traveled, that's a little bit different. When I talk about total distance traveled, if I'm moving to the left or if I'm moving to the right, what I'm interested in is how far have I traveled. Total distance traveled problems, you need to have absolute values. And so the total distance traveled by an object from A to B is actually going to be the definite integral of the absolute value of velocity. Another way to say absolute value of velocity, it's the speed. To find total distance traveled, you integrate the speed function from A to B. Let's look at an application problem. So I've given you the graph of a piecewise function over here at the right. The graph at the right displays the velocity for a moving object. I did not include units here. My apologies. Part A, on the interval 5 to 15, when is the speed of the object the greatest? So, first of all, I tell my kids to put blinders on. We're only looking from 5 to 15. Whatever happens outside that portion of the graph, we are not interested in. So, the first question is, when is the speed the greatest? Well, if I just look at the graph, a lot of mistakes will come in when somebody says, oh, the speed is going to be the greatest over here at 5 because I can see that is the highest point. Well, that's not good enough because the way we get speed is the absolute value of velocity. So if I look at the absolute value of the velocity at 5, I'm going to get the absolute value of 3, which is 3. But, let's see, over here at 12, If I were to find the absolute value of the velocity at 12, the velocity at 12 is -4, and the absolute value of -4 is 4. Since 4 is greater than 3, the speed at 12 is greater than the speed at 5. So my answer would be the speed is greatest at t equals 12. There are no units. Don't make them up. Just leave it. The speed is greatest at t equals 12. All right, part B. What's the acceleration of the object at t equals 6? Well, I want the acceleration at 6. The way we find the acceleration is the derivative of velocity. All right, well, how am I going to find the derivative of velocity? What I know about the derivative is the derivative represents the slope of the tangent line. So over here at t is equal to 6, I need to find the slope of the tangent line that I would draw there. And in this case, the tangent line actually lays directly on top of that curve. If I want to find the slope, all I need to do is pick 2 points on the line, and I'm going to pick this point here, and I'm going to pick the x-intercept. I go down 2 spaces, I go to the right 2 spaces. The slope of the tangent line is -2/2, which is -1. That's going to be the acceleration at t equals 6. Okay, part C. If the object has an initial position given by x of 0 is equal to 3, so that's my starting point, I want to determine the final position of the particle at t equals 13. Now, we're given the graph of the velocity, we're given a starting position, we want a final position. This is a classic time to use your the fundamental theorem of calculus. Sorry. So I need the position at 13. The position at 13 is equal to the position at 0 plus the integral from 0 to 13 of my velocity curve. The position at 0 is told to be 3. Now I need the area bounded by the velocity and the x-axis, starting over here at 0, going all the way to 13. Okay, so let's look at that. I need to find the area of this piece up here. I need the area of this piece over here. Let's break this up into regions that we can find quickly. If I look at the area from 0 to 4, we'll call that the first piece. That's just a rectangle. The length is 4. The height is 4. 4 times 4 gives me an area of 16. If I look at the region between 4 and 8, ignore this little line here that we needed that in a previous problem. I have a triangle. The height of my triangle is 4. The base of my triangle is 4. I take the base times the height, that's 16, cut it in half. Positive 8. Now if I look at the region from 8 to 13, it's not a triangle, it's not really a trapezoid. What we're going to have to do is we're actually going to split this into 2 different regions. Again, we're getting a triangle. So 4 times 4 is 16, cut it in half, that's 8. Because it's below the x-axis, we're going to consider that -8. This region over here, the fourth piece, is a trapezoid. I see that these 2 sides are parallel to one another. There's the base perpendicular to the heights. So that length there is 4. That length there is 3. For a trapezoid, you add the base lengths together to get 7. You multiply by the height, which is 1. And then you cut that in half, and so we're going to get a -3.5. So let's come back to the problem. What we've just discovered is that the area under the velocity curve from 0 to 13 is going to be 16 plus 8 minus 8 minus 3.5. When I combine all that, 3 plus 16 is 19, plus 8 is 27, minus 8 is 19, minus 3.5 is 15.5, and again, no units. Okay, let's go a little bit further with this question. All right, now I want to find the exact value from 4 to 12 of the velocity, and I want to explain the meaning of the answer. Okay, that seems easy enough. So I go from 4 to 12. I want the integral of the velocity, starting over here at 4, going until 12. I have a triangle up here. We've already determined earlier that that has an area of positive 8. Triangle over here has an area of negative 8. And so I get 0. So coming up with the numerical answer is great, but now we need to explain that. Because we found the integral of the velocity from 4 to 12, this means that my displacement from t equals 4 to t equals 12 is 0. It would be a mistake to say that tells you the object hasn't moved. I can see at t equals 4, I have positive velocity. That means my object is moving in the positive direction. I can see from 8 to 12, my object has negative velocity, so it's moving in the negative direction. If you say the particle hasn't moved, I would not award you the points. You could leave it as displacement from t equals 4 to t equals 12 is 0, or even better, you could say the particle has returned to its position at t equals 4. I think that would be a best case explanation. All right, let's look at E. E, average velocity of the object on the interval 1 to 15. I'm just going to do the setup and not actually finish this off. I want average velocity on an interval. This is where you're going to use your average value theorem. So we find the integral from 0 to 15 of my velocity. And I'm going to multiply that by 1 divided by 15 minus 0. The reason I'm stopping here, well, I guess we can make that 1/15. The integral from 0 to 15 v of t dt. We've already done several computations involving the area. You'll just find the area of the rectangle plus the area of the triangle, subtract the area of that triangle, and then subtract the area of this trapezoid. That's 4, that's 5. Wait, I think I'm doing this too quickly. That base is 4, that base is 1, that's 5. The length of the height there is 15, so we're going to subtract 7.5. You'll just have 1/15 plus that, 1/15 times this number plus this number minus that minus that. Sorry, I messed that up a little bit at the end there. Okay, other thing that we're exposed to in this unit is properties of integrals. So, again, we don't actually know how to compute integrals without using the calculator, but we did start exploring the properties, and we did this from a graphical standpoint. We just let our geometry skills kick in. So, I'm going to give you two functions on the interval a to b, and we're going to pick a point somewhere in between a and b, and we're going to let k be a constant. All of these properties are true. The first one says, if I find the definite integral from a to c of f of x, plus I find the definite integral from c to b of f of x, then it's actually the same thing as finding the definite integral from a to b of f of x dx. Let's get a little picture here. So here's f of x, here's some point a, here's some point b, and here's some point c in between. This first integral says find the area from a to c of that function. Well, that's this piece over here. That's piece number 1. And then we find the definite integral from c to b. That is this piece over here. The result says that I'm going to get the same thing as if I just found the definite integral from a to b. I think with this diagram in place, it's pretty obvious that if I take the separate regions, region 1 and region 2, the area that I get is the same thing as if I just found the area of that one region altogether. Okay. Number 2, here's the second one. The definite integral from a to b of f of x dx is actually equal to the opposite. So it's the negative of the definite integral from b to a, f of x dx. What that means is if I have some function, f of x, and I have endpoints at a and b, if I find the definite integral moving from a to b, all right, I'm going left to right, which is the way we normally think about our integrals. It is going to be the exact opposite of finding the definite integral from b to a. So we introduce that negative sign when you switch your limits of integration. And we've seen that show up a few times. Our third property, k is a constant. I'm asking you to find the definite integral from a to b of a constant. The result says it's k times b minus a. Let's look at a graph here. If k is a constant, then the graph of a constant is just going to be a horizontal line. Here's y equals k. If I find the integral from a to b, there's a, there's b. What I just created is a rectangle. The way I find the area of a rectangle is I take the height, which is k, times the length, which is b minus a, and I get k times b minus a is that area over there. We'll check that one off the list. Number 4, the fourth property, says that the integral from a to b of a constant times a function is equal to a constant times the definite integral of that function. The way we normally handle this when we use this in a problem, if you see that you have a constant times a function, then this property allows you to factor that constant out in front of the definite integral. I don't have a diagram to go along with that, but this is just the you can factor constants out in front of the integral property. We use that quite a bit, and it is really, really helpful. Property number 5, if f of x is less than or equal to g of x on an interval, so I have a function that point for point is always less than or equal to g of x. So I like to think this function is smaller than that one, then it should be true that the definite integral of the smaller function is going to be less than or equal to the definite integral of the larger function. If you need a diagram for that, I would draw something. Here's f of x. Maybe you get a different color pen, and here is g of x. If I look at it from a to b, the integral of f of x from a to b would be this blue region. The integral from a to b of g of x is the green region. And I can see pretty clearly that I have more green area than I have blue area. That's what this property over here is telling us. Property number 6, if I'm taking the definite integral of two functions being added together, that it is the same thing as finding the definite integral of the first function plus the definite integral of the second function. I like to think of this as I can take the integral sign and I can distribute it over addition. Integrate the first function, plus you integrate the second. We can also perform that same distribution if I have subtraction in between. So the definite integral of a function minus a function is the same thing as the definite integral of the first function minus the definite integral of the second function. Okay. Second property. Number 8. If f of x is an even function, think about y-axis symmetry. We're thinking about curves like y equals x squared, like y equals the absolute value of x, and a bunch of other ones. If I were to draw some function that has y-axis symmetry, and I find the integral from negative a to a, this area to the left of the y-axis is exactly equal to the area to the right of the y-axis. So I can just say that the total area is equal to double the area from 0 to a of f of x dx. Number 9, an odd function, you have rotational symmetry. Think about curves like y equals x cubed, y equals 1 over x. If I have an odd function, my odd function could look something like that. If I find the area from x equals negative a to x equals positive a, if this truly is an odd function, this area above the x-axis is positive. This area is negative. Because it's an odd function and I have that symmetry, these are going to cancel out, giving me a total area of 0. Be careful with these last two properties. Number 9 is only true for an odd function. Number 8 is only true for an even function. If you don't know even and odd, you cannot use these two properties. All right. So here are some problems that we looked at in class, and these are pretty typical problems that you're going to see, especially in the multiple choice part. I've told you that the definite integral of f of x dx from 0 to 1 is equal to 4. Further, I've told you that the definite integral from 1 to 2 of that same function is 8, and that the total area under f of total area from 0 to 3 of f of x is equal to 11. Given those 3 bits of information, we're going to solve some, but not all, of these other problems. So the question asked about the definite integral from 0 to 2 of f of x dx. Well, if I want, I could say that the definite integral from 0 to 2 is the same as the definite integral from 0 to 1 plus the definite integral from 1 to 2. The definite integral from 0 to 1 we know is 4, plus the definite integral from 1 to 2 is 8. So in total, the definite integral from 0 to 2 is 12. That's that. Let's jump over here to the second one. I'm now being asked to find the definite integral from 1 to 3 of 4 times f of x. That 4 is a constant. I'm allowed to factor that constant out. So now I have 4 times the definite integral from 1 to 3 of f of x dx. Now, if I'm going to find the definite integral from 1 to 3, I wasn't given that explicitly. I'm going to have to get a little creative, and so how about this? I'm going to say the definite integral from 1 to 3 is the same as the definite integral from 0 to 3, and I'm going to subtract from that the definite integral from 0 to 1. Total area from 0 to 3, if I subtract or knock out the area from 0 to 1, what I'm left with is the area from 1 to 3, which is what I wanted. So I have 4 times 11 minus 4. I'm getting 28 as my total area there. This number 3 is pretty similar to the other ones. Try that one on your own. Number 4, let's look at this one. I've got the definite integral of f of x plus 3 dx. I have a function plus a constant. The way I'm going to handle this one is I'm going to distribute that definite integral. So it's the definite integral from 0 to 2 of f of x dx plus the definite integral from 0 to 2 of 3 dx. This part here, we've already determined in problem number 1. We know that that's 12. We've got to add on to that this expression. Well, the definite integral from 0 to 2 of 3. When we say that, we're looking at the line y equals 3 from 0 to 2. The total length there is 2. The height is 3 for a grand total area of 6. So now I have 12 plus 6 is 18. Let's see another way that this could show up. Number 5. I want the definite integral from 0 to 2 of f of x plus 3x. I'm going to make that the definite integral from 0 to 2 f of x dx. We've seen that already. The definite integral from 0 to 2 3x dx. I know that that part there is equal to 12. Now, the integral from 0 to 2 of 3x, 3x is not a constant. It's not like number 4. What I know is that if I graph the line y equals 3x, it'll pass through the origin, so I have the point 0, 0. It also passes through the point 2, 6. And if I want the definite integral from 0 to 2, all you need to do is find the area of that triangle. The length of the triangle is 2. The height of the triangle is 6. Clearly not drawn to scale. 2 times 6 is 12. Cut it in half, you get 6. And we get 12 plus 6, 18. Okay, so now let's look at number 6, and I hope to do this one well. So, I want the definite integral from 4 to 6 of the function f of x minus 4. Now, way back in Algebra 2 and in pre-calculus, we learned that this just is a shift of f of x 4 spaces to the right. Well, I don't know what f of x is, but I do know that the area from 0 to 2 of f of x dx, we figured out earlier that that's 12. The graph of f of x minus 4 would just mean to take that whole graph that we were just looking at and shift this 4 spaces to the right. So, where I used to have this point at 0, that's been shifted 4 spaces to the right. This guy over here at 2, I'm also going to shift 4 spaces to the right. And I'm just going to take that function and I'm going to shift the whole thing over 4 spaces to the right. This region over here is this region over here on the graph of f of x minus 4. So if the area was 12 in the graph before it was shifted, it's now 12 after the shift. All right. Gosh, it seems really incomplete to leave number 3 there. I don't like that. So let's finish off number 3. The definite integral from 2 to 3, I'm going to start by the definite integral from 0 to 3. And then I'm going to subtract off the pieces I don't want. I don't want the area from 0 to 2. So 0 to 2 f of x dx. The definite integral from 0 to 3 is 11, minus the definite integral from 0 to 2 is 12. So my final answer is -1. Sorry, I just cannot stand to leave that one incomplete. All right, so those are all the big ideas that we encountered in the unit. What we're going to look at in the next video, but I need to stop this installment, is one application problem. There's actually, it's a really nice problem. We've done a lot of these in October, November, December. These are really common on the AP exam. The situation is we have sand being poured into a bin that you're told initially contains 100 cubic meters of sand. During the workday, for 0 less than or equal to t less than or equal to 10 hours, the sand pours into the bin at that rate over there. S of t is 5,000 divided by t cubed plus 50 cubic meters per hour. After 1 hour, the sand is removed from the bin at a rate given by r of t equals 23.967 square root of t cubic meters per hour. And then there's a bunch of follow-up questions. I'm going to stop this portion of the video right now. What you'll need to do is get your calculator and move on to video 2 with me in a little bit.